Good morning. My name is Utkarsh Chauhan and my topic today is reward circle. These are the headlines we are covering today. What is a reward? Anatomy of the reward system, complex behavior and the reward pathway, and the concluding thoughts. Introduction to the concept of reward. What is a reward? Uh, an appetitive stimulus given to alter a behavior, an objective way to describe the positive value that one ascribes to an object, behavioral act, or internal state. Food, sex, endorphin rush from exercise could be the examples of reward. Now, the anatomy of the reward system, we will be covering in three headings. The critical role of dopamine, overview of the reward pathways, the functional neuroanatomy of the reward system. The critical role of dopamine. The reward system is one of the major dopamine pathways in the brain, often referred to as the dopamine reward system. Reward properties of drugs are all tied to the dopamine. Now, in the given diagram, we can see some drugs like nicotine, cocaine, and amphetamine directly increase the dopamine levels in the synaptic cleft, whereas there are drugs which indirectly increase the dopamine levels. The ventral tegmental area, midline floor of the midbrain, receives input from the subcortical attention area, median forebrain bundle, bundles of the dopaminergic neurons, which connects the ventral tegmental area to nucleus accumbens and the limbic system. The nucleus accumbens is a part of ventral striatum, and the limbic system, the median forebrain bundle projects to the olfactory tubercle, innervating the septum, amygdala, and hippocampus. The mesocortical pathway, it consists of starts at the ventral tegmental area, prefrontal, cingulate, and perirhinal cortex. Now the functional anatomy of the reward pathway. Reward prediction, error signals, incentive salience, reward euphoria, and anticipation of reward and habit formation. The reward prediction error signaling. Initially, dopamine neurons in the ventral tegmental area responds to presence of a reward. If a sensory cue predicts reward, dopamine neurons fire in response to the cue, not the reward. If a reward fails to occur, dopamine neurons decrease firing. Unexpected rewards result in higher dopamine release and greater learning. Now the incentive salience. The mesolimbic pathway enhances the motivational properties of the cues predictive of reward. Motivation is associated with the amygdala. This property is referred to as incentive salience. Motivation states increase the incentive salience of reward and related cues. Now the reward euphoria, where the high comes from. The nucleus accumbens, most researches in this includes the cocaine and amphetamines. Both causes substantial increase in the synaptic dopamine levels. Blockade of dopamine in the nucleus accumbens decreases reinforcing effects in animals. Anticipation of reward and habit formation. There are reciprocal connections from the prefrontal cortex and hippocampus, drive anticipation and craving. Reduction in executive functions can contribute the incentive salience of drugs and other artificial rewards over natural rewards. Now the complex behaviors and the reward pathways, drug use and abuse, gambling, subjects given L-DOPA at spotting winning strategies. During investment, anticipation of gain activates nucleus accumbens. During shopping, product preference associated with nucleus accumbens. Now this is the neurobiology of addiction. and various pathways included in it. The preoccupation, anticipation, craving, binge intoxication, and withdrawal negative effect. Now, final thoughts. The reward system can downregulate due to repeated exposure to a reward, reducing the feeling of a reward. Disruption of the reward system can result in anhedonia. Not all rewards are the same magnitude. My references. Thank you.
Good morning all. Myself Vasundhara Pandit and I'm presenting the topic inhibitory control circuit. So in this topic, I will mainly talk about GABA. Gamma aminobutyric acid is the main inhibitory neurotransmitter in the brain. GABA is produced from amino acid glutamate with the action of enzyme glutamic acid decarboxylase. Once formed in presynaptic neuron, transported into synaptic vesicles by vesicular inhibitory amino acid transporters, where it is stored. So in this slide, GABA is produced by amino acid glutamate with the actions of enzyme glutamic acid decarboxylase. Termination of action. GABA synaptic actions are terminated by presynaptic GABA transporter, also known as GABA reuptake pump, analogs to similar transporter for other neurotransmitter. GABA action can also be terminated by the enzyme GABA transaminase. GABA receptors. There are three major types of GABA receptors: GABA A, B, and C. GABA A and C are both ligand-gated ion channels, while GABA B are linked to G proteins. So there is two types of inhibition, that is phasic and tonic inhibition. Benzodiazepine sensitive GABA A receptors, those contain gamma, alpha 1 and alpha 3 subunits, are postsynaptic receptors that mediate phasic inhibition, which occurs in bursts triggered by peak concentration of synaptically released GABA. Benzodiazepine insensitive GABA A receptors, those containing delta subunits and alpha 4 and alpha 6 subunits, are extrasynaptic and they capture GABA that diffuses away from the synapse. GABA is implicated in a large number of diseases, including anxiety, stress disorders, pain, musculoskeletal disorders, sleep disorder, depression, addiction, withdrawal syndromes, seizure syndrome, encephalopathies, hepatic disorders, memory and learning disorders, hormonal disorders such as premenstrual syndrome, convulsive syndrome. So many studies have shown that there is a role of GABA in decrease of inhibitory GABAergic tone is associated with an increase in neuronal excitability that favors the hypersynchronization of neuronal electrical activity and the appearance of convulsive episodes. This can trigger numerous pathological processes such as epileptic states, state GABA and anxiety. The brain circuits and amygdala are thought to comprise inhibitory networks of gamma aminobutyric acid interneurons. This is this neurotransmitter thus plays a key role in modulation of anxiety responses, both in normal and pathological state. The presence of allosteric sites on GABA receptors allows the level of inhibition of neurons in the amygdala to be regulated with exquisite precision. GABA and depression. The result derived from various research tools support that the presence of deficiency of GABA system in major depressive disorder, which appears to be restored by common antidepressant treatments. And since neuroactive steroids have antidepressant properties, this has led to the proposal that some depressed patient may have a lack of normal tonic inhibition and thus too much excitability in some brain circuits. Hypothetically, this could be calmed by neuroactive steroid administration, causing more efficiency of information processing in those brain circuits and reduction of these symptoms of depression. GABA and epilepsy. So, abnormalities of GABAergic function have been observed in genetic and acquired animal models of epilepsy. GABA agonists suppress seizures and GABA antagonists produce seizures. Drugs that inhibit GABA synthesis causes seizures. Benzodiazepine barbiturates work by enhancing GABA-mediated inhibition. Drugs that increase synaptic GABA are potent anticonvulsants. Two recently developed anti-epileptic drugs, vigabatrin and tiagabine, are examples of such agent. However, their mechanism is quite different. Vigabatrin is an irreversible inhibitor of GABA transaminase, whereas tiagabine blocks GABA reuptake into neurons. So, the first sedative acting agent produced more than 100 years ago act on GABAergic system, namely barbiturate, substance derived from barbituric acid. GABA-A agonists include barbiturates, phenobarbital, benzodiazepine, diazepam, imidine, flurazepam, alprazolam. So in this table, here are certain drugs which alter the mechanism of GABA, that is valproic acid, which is the blocker of GABA synthesis, reduces GABA synthesis and reduces the inhibitory tone. Pyridoxine, which is activator of GABA synthesis, increases GABA synthesis. Valproic acid also prevents transport of GABA, increases inhibitory tone. It also inhibits the degradation of GABA, prevents GABA reuptake, increases inhibitory tone. Benzodiazepines, barbiturates are the agonist of GABA-A receptors, increases chlorine entry by GABA-A receptor, and they increases the inhibitory tone. Antagonists of GABA receptors are flumazenil, that decreases chlorine permeability, reduces inhibitory tone. GABA-B receptor agonist, baclofen, increases potassium output, and antagonists, seclofen, reduces inhibitory tone. So here are the references. Thank you. Good morning, everyone. My name is Vaishnavi, and I am presenting the topic on motivational circuits. Motivation means that which moves the will. It is a factor in most of the behaviors. Thus, those processes which are responsible for goal-directed quality of the behavior are the motivations for behavior. Motivation allows the brain a way of setting priorities. Motivation could be described as the ability to make predictions about what is the most important in particular scenario. Motivational drives can be external or internal. Internal stimuli or external stimuli, motivational states leads to the evaluative functions, which can be a representation, valuation, cost, benefit, and conflict analysis. Effector functions, prediction, action selection, error monitoring. Goal-directed behavior, which can be approached to a particular process, or inhibition or fight or flight, or goal attainment. Internal and external survival drives. Internal drives tends to be coordinated by the hypothalamus from the internal sensory inputs, while the external drives tend to be coordinated by the amygdala from the external sensory inputs. Internal derives like energy balance, water balance, or circadian rhythms, stress responses, reproductive behaviors, or defensive behaviors. External derives comprises of response to the outside threat, response to reproductive opportunity, response to social situations, or parental attachments. The circuitry of motivation consists of three pathways: hypothalamus and homeostatic derives, amygdala and external world derives, and midbrain dopamine neurons, and the common currency of the motivation. Hypothalamus and homeostatic drives. The hypothalamus is important for maintaining homeostasis. It collects information about the internal state of the body and initiate responses. There are many different nuclei within the hypothalamus. Some seems to be predominantly input, while others are mostly output nuclei. The hypothalamus involved in the wide range of behaviors. Hypothalamus is connected directly with the nucleus accumbens and indirectly with the prefrontal cortex, hippocampus, and amygdala, all of which are a part of brain's motivational architecture. These connections direct the autonomic, endocrine, and motivational aspect of the homeostasis. Amygdala and external world drives. Sensory system project to the amygdala, which monitors the external world. Output options of the amygdala include autonomic responses, neuroendocrine responses, or behavioral responses. The basolateral amygdala responds very rapidly to the threatening stimuli from the external world. The centromedial amygdala coordinates the responses of the other areas to the sensory stimuli. This picture shows the amygdala that contains several nuclei. This coronal section of the brain depicts the location of the amygdala and some nuclei within the medial temporal lobe. Basolateral nuclei take sensory input from the thalamus and cortex, while the central and medial nuclei send behavior regulating outputs to the brainstem, the hypothalamus, and indirectly to the prefrontal cortex. Midbrain dopamine neurons and the currency of motivation. The nigrostriatal pathway projects from the substantia nigra to the striatum and is the most important for motor control. The mesocortical pathway projects from the ventral tegmental area to the prefrontal cortex and is important for the cognition. The mesolimbic pathway projects to the cingulate cortex and is important for the emotional regulation. This picture shows the two areas which are important part of the midbrain dopamine network, that is the ventral tegmental area and the substantia nigra. These are the references. Thank you. Any questions? Normal डिप्रेशन और ग्रीड में क्या फर्क है? तो आपने टेबल को प्रेजेंट किया, पर ऐसे अगर आप बोलना